So the last vector multiplication, the last product of vectors, is what's called the dot product. I'm going to take a few seconds to write down what we already know. What we know is that a vector times a scalar gives me a vector. Always gives me a vector. Okay? A vector crossed with another vector gives me another vector. And then there's the business of these vectors are perpendicular to each other, and this vector is going to be perpendicular to the result of those two vectors. Okay. Last one is the dot product. Vector dotted with another vector gives you a scalar. Okay? So, normal, a vector multiplied by a scalar gives me a vector. A vector crossed with another vector gives me a third vector. And a vector dotted with another vector gives me a scalar. Now, let's talk about the mathematics of the dot product. Now, the most common vector, or the most common use of a dot product, excuse me, it's a little hot here. The most common use of a dot product is work, okay? And I'm not going to fully explain work, but the idea of work is applying a force over a particular amount of distance, and actually the proper term is displacement. So you're applying a force over a particular amount of displacement. And displacement is just keeping track of direction. Okay, distance doesn't do that. Okay, and that's what we call work. So let's imagine that you're pushing a car. Here's my car. And you're pushing it with a particular amount of force. But the force that you're applying is in this direction. Okay? For some reason, you're pushing up on the back of the car as you're moving it. Now, you can easily do that. As a matter of fact, in some cases, that's the easiest way to move objects, is like partly pushing them up and over. Okay? But this is the direction in which you're going to push. Now, we all know that you're not going to push that end of that car up unless you're the Hulk, or another superhero of some sort. So we all know that the car will roll, but it's going to roll in this direction. We're going to call that displacement. Now, this is the difference between IB and AP right here. Part of the difference. When you're talking about IB, displacement is an S. When you're talking about AP, displacement is a D. Okay, enough said. So the amount of work you're doing is the amount of useful force that you're applying times the amount of the displacement that it's going. Okay, does that make sense? So you're concentrating on how much of that work, that force that you're applying, is actually useful in moving that vehicle and in the direction of, and then multiplied by the displacement that it travels in that direction. Okay? That's what work is about, and that's actually what the dot product is about. So force dotted with displacement. Now, once again, for IB, that's force dotted with displacement. Okay? They use an S for displacement. Cool? Now, in an ideal situation, you're going in the same direction. Okay? But what if we weren't? What if in my example I'm applying a force up? I'm looking for a value where if theta is equal to 0, where I'm pushing in the same direction as my displacement, that my result is going to be 1. What trig function says that if theta is equal to 0, then it's equal to 1? Well, that's a cosine. Okay? So the generalized term for that is force dotted with displacement. Well, let's not say dot. Well, let's say force dotted with displacement equals force displacement cosine theta. Cool? So that means if you're pushing in the same direction, that turns into 1 and you do your maximum amount of possible work. Okay? It also means something else. That if you go with a force in this direction and a displacement in this direction, you get a negative work. The difference between those two vectors is 180 degrees. The cosine of 180 is negative 1. So that would end up with negative force times distance. Well, that's good. If you think about it, in the case of a car, the car is moving in this direction, right? And you apply a force in this direction. What you're actually doing is you're slowing the vehicle down. You're doing negative work on it. Okay? You're not making it go any faster. It's only when both of those vectors are pointing in the same direction do you do positive work. You're moving the car along faster. So when dealing with dot products, it's important that you realize that anti-parallel, which means that one vector is pointing in the exact opposite direction of the other vector, results in negative work. Where parallel, where both vectors are pointing in the same direction, results in positive work. Now, it's really kind of cool when you actually get into work and you talk about gravity, because gravity is a wonderful thing. It does positive and negative work all the time. Okay? So when dealing with cross products, or not cross products, dot products, it's important that you keep track of that direction. Is the force pointing this way and the displacement this way? Negative. Okay? If they're anti-parallel, negative. If they're parallel, they're positive. Okay? And then the generalized form is going to be vector A times vector B cosine theta. Now, the really cool thing about this is that I never said anything about direction. We're not concerned about direction. As a matter of fact, the way mathematically it's done to talk about work is talking about an integration. So if you had a force vector in this direction and the motion of that object, its displacement, does something like this, you have to sum up all of this positive and all the negative displacements in that direction. It's not keeping track of the direction that it travels. It just simply looks at how much you go in that direction. You multiply them together. Okay? You end up getting a scalar, which is great because it turns out to be energy. Energy is wicked cool. Okay? Cool? Dot products. Vector times vector gives me scalar. The generalized form is going to be vector 1 times vector 2 times the cosine of theta. And the most common dot product that we'll be dealing with is going to be work. All right.